On today's episode, Saab flies the first 3D printed battle damage repair part and a different kind of grid-scale battery, artificial intelligence. Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on engineering.tv today. Stockholm-based aircraft maker Saab has announced another first for 3D printing: repair panels for battle-damaged jet fighters. The company flew a Gripen jet over the company's test base in Linköping, Sweden, with an exterior access panel made using additive manufacturing. The material used was the polyamide resin PA2200, similar to the familiar nylon. Making parts with additive manufacturing is not in itself new, but what made this test different is that the replacement part was made with no 3D computer model of the original component. The existing part was scanned and duplicated by the 3D printer, simulating a forward-base battlefield repair scenario that would be encountered in combat operations. The part was also significant in that it was an aerodynamic surface. Additive manufacturing is used for internal components on the Gripen and in many other aircraft programs, but it's rarely seen in structural or aerodynamic applications. The Gripen is considered to be an advanced fourth-generation jet fighter without the stealth of a fifth-generation aircraft like the F-35, but carrying an advanced suite of electronics for multi-role operations and capable of operating without the very large logistics tail needed by fifth-generation fighters. Spare parts availability is a major factor in determining aircraft uptime, and it's not uncommon for maintenance personnel to cannibalize existing aircraft to keep others flying. Post-flight inspection of the 3D printed hatch on the test aircraft showed no problems, and the company is working on a containerized additive manufacturing system that can be easily deployed to forward bases. Next steps will be the development of other materials, including resins optimized for the extremely cold temperatures of high-altitude flight. The system is part of Saab's sales strategy for the Gripen program, which emphasizes ease of maintenance, fast aircraft turnaround, low cost, and the ability to use austere bases. Not said by Saab is what this technology implies. By disconnecting the part-making process from the need for CAD files or preloaded M-code, little would seem to stop Saab from making parts for any aircraft, anywhere. We'll be watching as this interesting technology develops. The recent Texas blackouts, well, they've thrown a Klieg light on power grid resiliency in America and around the world. Now, as the world transitions away from fossil fuels, detractors of clean energy solutions cite grid resiliency and supply certainty as serious issues with renewables. The World Economic Forum has been warning about the economic consequences of handling the transition poorly, and the organization has published a significant review written by Emmanuel Lagarrigue, Executive Vice President and Chief Innovation Officer at Schneider Electric. Lagarrigue's paper, put simply, states that any global transition to renewable energy will have to be managed by artificial intelligence. The premise is simple. Clean energy in the form of sources like the sun, wind, geothermal, and tidal power are decentralized, and generation may occur at the point of demand or thousands of miles away. Matching supply to demand with current heavily centralized technologies means peaker plants or throttling of existing generating capacity as system load varies. In a highly decentralized system where thousands or perhaps millions of energy consumers are also net producers of power at certain times of the day, matching supply and demand isn't so easy. But that decentralization is happening, he reports. In Australia, 30% of the country's residential, commercial, and industrial buildings will be equipped with solar panels by 2030 and 60% by 2050. In Europe, 36 million solar panels, electric vehicles, and energy storage batteries will be tied to the grid by 2025, and 89 million by 2030. One effect of this decentralization is the reduction in size of new power plants. In Europe, median plant size has fallen from 800 megawatts in 2012 to 562 megawatts in 2020, with some analysts predicting a fall to approximately 300 megawatts per plant by 2050. With millions of individual consumers also producing power and feeding it into a common grid, managing supply, load, and billing will require higher-level monitoring and management than current systems provide. AI is a natural technology for this, but as Lagarrigue notes, there is no legal or regulatory system in place to set rules about how a decentralized system will be managed. For large power utilities, which often revolve very significant long-term debt, the inevitable reduction in revenue as more and more of their customer base generates their own power means an inevitable switch to new sources of revenue. They may arbitrage power by buying it wholesale from individual producers, then reselling with a markup, or they may add fees or tolls for grid connection and the use of their AI-enabled management solutions. Another possible model is nationalization of power grid control systems by states, while letting markets determine electricity supply and demand. No matter which model is used, storing energy by using a national grid instead of local battery storage, well, it could reduce the cost of entry for homeowners and small-scale power producers, if governments get the rules right. Well, that's it for today's episode of This Week in Engineering, brought to you by engineering.com. If you like this show, be sure to subscribe to our channel and click on the notification bell for our next episode. For deeper engineering content, visit engineering.tv for exclusive shows like Manufacturing the Future and Designing the Future, not found on our YouTube channel. Thanks for watching.